for Module 3.1, the first lesson in here, the Ready, Set, Go is a little bit of what we've done and a lot of review. For number 1 through 5, we're going to be looking at, is it an arithmetic or geometric sequence? And then we need to create the equation for the sequence that we see, the pattern that we see. And off to the side, I would just want to make sure that we know, I'll give myself a little bit of space here. An arithmetic sequence has a recursive equation. So that, digging way back into the memory bank, recursive gives us our next step. So we need to first define our first step. And then after that, to find any step, we'll take the step right before it and add the difference between the first and the second and the third, and continue on. So we'll add the difference to get to that step. If it's a geometric sequence, so we're multiplying, we will again define our first step, and then to find our next step, take the one right before it and multiply that common ratio. So looking at number 1, goes 2 to 4, 4 to 8, 8 to 16, 16 to 32. This is just like in the lesson that we were working in. We got a similar pattern. We can continue on and say 64, 128, 256, and we know that because every jump we make has a common ratio of 2. Because we're multiplying, we know that it's geometric, and based on that, I have everything that I need. I need to define what my first term is. So my first term is 2. And every next term, I'll take the one right before it and multiply it by 2. For number 3, taking a look at how these jumps are made, we notice that we've got a negative and then another negative here, but then in between we've got positives. So the big thing to realize and understand there is that we're alternating negative, positive, negative, positive, negative, positive. And how we get that is by multiplying by -3. And I'm going to use a dot instead of the x because that looks like x minus 3. So if I take 81 times -3, negative 243. And if I take negative 243 times 3, I get 729. And you'll notice that these are continuing to alternate, going negative, positive. Taking that times -3 would give me negative 2187. And just got to do it one more time. 6561. Use a calculator to verify that I'm right. Maybe I'm not. So the type of sequence is yet again geometric because I'm multiplying. And that equation, don't worry about all this stuff. The equation doesn't depend on the 5th, 6th, 7th, 8th step. It really is looking at the first and how it moves. So the first step, the first term is -3. And to get any next number in this pattern, we'll take the one right before it and multiply it by -3. For number 5, all right, looking at number 5, things get really weird. -9, -2, 5, 12. But wait. If you look between the third and the fourth, from 5 to 12, you'll see, well, there's a difference of 7. Let's try this. -9 to -2, well, that's also a difference of 7. And if you were to take 7 and add it to -2, it would also, I know it's a kind of a roundabout way of doing it, but it might be a little bit easier for some of us to see where that pattern falls in rather than trying to start at -9, then go to -2, +5, and then +12. So continuing on that trend, we just keep adding 7. And since we're adding, we know that this is arithmetic. And our equation would need to define our first term. It's -9. But then every next step, we're going to take the one right before it and add 7. For number 6, you've got the value of f of 2. So here's the thing about f of 2. That is your output. That is your y value. So what is the value when x equals 2? What is the y value? So you can look on the graph and you can see at x equals 2, your graph has a y value. Whoa. F of 2 is 2. Now instead of doing 8, because that's much like 6, I'd like to do number 7. So find where f of x equals 4. So now you need to find out where this graph, where the y value is going to be equal to 4. So I'm going to look here, go across. Sure enough, when f of x equals 4, the x value is also 4. For number 10, I'm not going to do this whole thing for you because I did it in class with all of my students. But what I can offer up for those of you who were not in there is to set up an input-output table. Look to see where it crosses 0. Look to see where 2. Well, we know 2 goes to 2. We know 4 goes to 4. Look about 6. What about 8? I will tell you, it is not 2, 4, 8, or 2, 4, 6, 8. It's something to look at as you're going, and from there you should see a pattern that looks a whole lot like the work that you've already done today, or when you did the lesson. For numbers 12 through 14, this is what the lesson itself entailed. So I'm not going to go over all of them again, but I'll go over 12 and 14. Number 13 has the thirds. It's a little bit more challenging. But number 12 and 14 is along the lines of what the first portion of the lesson was about. So the difference, triple at each whole year. So 2, then 6, then keep multiplying by 3. And now we need to figure out what's in the middle. Well, 2 plus 6 divided by 2. So 8 divided by 2 is 4. 6 plus 18 divided by 2 is 12. 18 plus 54 divided by 2 is 36. And 54 plus 162 divided by 2 is 216. Number 14 grows by a factor of 4. So each next step you're going to multiply by 4. 480, so 512. And just like we did in number 12, find the average between the two. All right. There we go. So that's 12 through 14. And just giving you an idea of how to go about setting these up. Yes, in one of these, there is a mistake, and that's intentional. I want you to think about this. Go back and check to make sure. Do all these numbers make sense? For the go portion, I know that I cut off 19 and 20 here a little bit, but for the go portion, simplifying exponents. 3 to the second times 3 to the fifth could be written as 3 times 3, and then 5 more. 1, 2, 3, 4, 5. Count them all up, you would have a total of 7. You can also rely on the fact that when we're multiplying bases, we can add the exponents. So we can say 3 to the 2 plus 5. Well, 2 plus 5 is also 7, and verifies what we have. Number 16, 5 to the third, 5 times 5 times 5 over 5 times 5. Cross out what you have pairs for. Okay, they divide out to 1, and you end up with 5. You could also go about this saying that 5 to the 3 minus 2 is 5 to the first, which is also 5. Number 17, 2 to the negative fifth power can be rewritten as 2 to the fifth power underneath a 1. So 1 over 2 to the fifth power. Number 18, any non-zero number raised to the power of 0 is 1. That's it. Number 19. Again, it's cut off a little bit. Apologies for that, but I wanted to make sure I got everything in here. A few ways you can go about doing this. One of the ways is to write out all the 7s that you have here. I'm going to use some things that I know about number 15 and number 16 on number 19. So in number 15, it said if I'm multiplying the same base, I can add the exponents. So I'm going to take 7 to the 5 plus 3 over 7 to the 2 plus 4. Okay, because those I can multiply those same things together. And I would get 7 to the 8th over 7 to the 6th. Then, for number 16, if I've got them dividing the same base, I can subtract the exponents. Well, 8 minus 6 is 2. I would end up with 7 squared. The same process for number 20. 3 to the negative second times 3 to the fifth would be 3 to the third over 3 to the seventh. 3 to the 3 minus 7 would get me 3 to the negative fourth. And just like in number 17, I've got a negative exponent, so I flip it and change the sign. Hopefully this helps. Reach out if you have any questions.